Welcome to another video explaining the universe using the particle model. Today's video is titled Three Forces, Not Four. I've been covering several topics, a list of words, laws, constants. I did a lot on velocity, c of light. Today is on forces. Recently I had a viewer ask if I could explain polarization, and I thought, well, yeah, I've done that, but I couldn't find the video. So next time I'm going to answer the gentleman's question. I gave him a short answer in the notification where you click on the bell. You can ask questions or write a comment. And I did give him a short answer, but next time I will give a talk on polarization of light. Okay, so four forces. This is what modern science says. There are four forces. There's the strong nuclear force, the electromagnetic force, weak nuclear force, and gravity. It's interesting, they give a relative strength of these forces. The assumption is that the strength of the gravity force, it says really weak, but it must be 1 relative to these other numbers. The weak nuclear force is 100 nonillion times stronger than gravity. And the electromagnetic force is 1,000,000 times stronger than the weak force. And the strong nuclear force is 1,000 times stronger than the electromagnetic, which is 1,000,000 times stronger than the weak force. And that's nonillion is 10 sets of 3 zeros, so that's 32 zeros in that. Now, they do give you an explanation of what the strong nuclear force is, and it has a name, a gluon, and it holds the nucleus together specifically to overcome the electric force. The electric force, which if you have two protons, if the two red ones are protons, they should separate, blow up, repulse each other, and they don't, and so they make up this strong nuclear force which holds them together anyway. And then the electromagnetic force, they say, is the force carrier is the photon. The photon is in here. That's what they say. And then the weak nuclear force is the W and Z bosons, and these are force carriers, not particles, but they have these names. And of course, they have gravity, which they call the graviton, but they have not yet discovered it. These are the four forces of science. The title suggests, well, maybe there's only three. But they do combine electroweak with the the electromagnetic force, and the weak force get combined together. One of the major discoveries of the 20th century has been that these two forces are different facets of a single, more fundamental electrical weak force. And they're much different. The electromagnetic force goes a long way. The weak force is short range, and somehow they are able to combine it in whichever way they do. And a lot of people have been looking for a grand unification theory, getting all these forces put together as if there was one magic force that does everything. It says, because the macroscopic world offers numerous opportunities for particle unification, there have been a number of grand unification theories proposed, none of them considered to be universally accepted. There is even a theory involving this gut theory that includes all fundamental forces being merged together at higher energy levels. It is often referred to as the theory of everything. Oh, they're trying to do all things. They'd love to have that one theory of everything that explains it all. Well, the particle model, well, it has two gravity forces. Well, no. Theoretically, there is an infinite number of levels in the particle model and therefore an infinite number of gravitational forces. However, only two are used to describe physical events that we see today that I've had to explain. Someday we might find evidence of a third gravity. So there are two forces of gravity, gravity 1, gravity 2, and one magnetic force. Now, here's an interesting point. They don't talk about, when they talk about forces, it isn't about mechanical, they don't say mechanical forces. Newton invented the idea of force, and or at least he quantified it with his second principle and his theory of equation for gravity. And the forces that we feel with wind and water, they don't talk about these. These forces are the forces you can't see. Here's a interesting graphic that I came upon just before it was yesterday. And it talks about the classes of forces, and I added this comment: all of them are pushes. Here you have what they call contact forces, and these three. Two are pulling, and one is pushing. Here are the second group of the field forces. Now, this is the group that we're talking about here, the modern science with their four forces and the particle model with three. These are forces you can't see, but we know they're there. You can feel them or experiment with them. So you know they're there, but you can't see them. These are something you can see, feel, whatever. All of them are pushes. No, they're saying this is a pull. And if you were to tell your student to test this and see what kind of force is needed, you could put a scale on that thing and pull it with a scale and measure the force that it takes to pull that spring out maybe 6 inches. But in reality, the fingers are behind the handle, and the fingers are behind it. You're pulling this object. My other hand, I pull my other hand toward me by pushing it. You're really pushing the handle towards you. She's doing the same thing with the wagon. And of course, this is very clear. The football player is kicking and pushing the football. All of them are pushes. It's sort of a side point. When I ran across this, I thought it'd be interesting to show. But let's talk about G1 gravity, with the first one of the forces, and this starts with the G1 gravitic field. And what is that? Well, the G1 particles are emitted randomly from level 1 atoms that are in the stars of the universe. And there are 76 trillion, an estimate of 76 trillion stars in the observable universe. All these stars are combusting at all kinds of levels, in particularly level 1 atoms, mostly hydrogen, and they're being emitted randomly in all directions. That's what the TPM calls the G1 gravitic field. But there is no net force of G1 gravity unless there's a level 1 object in that field. So you got to bring a level 1 object, bring in the Earth, and it's the combination of the G1 gravitic field and the Earth that sets up a gravity field around the object. You got to have two things, not just one, just to get the field around the object. And this is a diagram. I've shown many of these before as to how you generate the G1 particle. I have symbolically 5 coming in, 2 of them hit and push. They push the Earth, and you're left with 3 coming out against 5 coming in, and it's the net 2. You have 2 more pushing down than you have 2 more pushing down. That's the net force. And this G1 particle moves at speed c1. That's a new term I'm starting to use. C1 is the orbital speed of level 1 atoms. So that's how you set up gravity. You got to have the G1 gravitic field and an object. G2 gravity, you start with the G2 gravitic field. G2 particles are emitted randomly from subatomic atoms that are in the stars and in the universe. Well, modern science doesn't even talk about subatomic atoms, and it's a postulate that the particle model makes in order to have a particle moving faster than the G1, and that's when you get involved with the magnetic field. So we'll cover that in a moment. G2 particles are emitted randomly from subatomic atoms that are in the stars. They're combusting along with the other atoms and being sent out in all directions. Again, there is no net force of G2 gravity unless there is a level 1 object. There's a level 1 object in that field. It is the combination of the G2 gravitic field and a level 1 object that sets up a gravity field around the object, a G2 gravity field. And the G2 gravity primarily is the nuclear binding force. That's the strongest force that they talk about. We don't call it the nuclear binding force. It's not a gluon. It's the G2 particle, which is the orbital of the subatomic atom. It also, if it can bind the nuclear, it also binds the atomic, the G1 to the atom, and it holds atoms together. Again, they say that the two protons would repel each other because of the electric force, so they need a strong nuclear force. Particle model does not have charge. All we have are nucleons. We call them, at level 1, we call it the N1. And it's G2 gravity that surrounds this and holds the nucleus together. And so the point being, I said in the G2 that when you surround a level 1 object, and the fact is, as drawn here, I added to the G1 forces involved with the Earth, G2 forces. Now, both of them are all the way around in all directions. It isn't just in two direction. It isn't just XY direction, but the in and out is also included. All directions. G1 gravity acts gravitationally with level 1 atoms around the Earth, and what does it do? Holds the atmosphere in, holds the water in, holds us in. That's what keeps us together. Gravity 2 acts gravitationally with level 2 and level 1 atoms that are in the Earth. And what does it do? Well, when light comes from the sun, when light comes this direction, hits the atmosphere, it refracts, and blue is generally bent more and comes down into the surface of the Earth. And that's why we see a blue sky, and it's G2 gravity that does that. It bends the G1 particles, light. TPM light is coming from the sun, gets bent and refracts and gives us a blue sky. Okay, the magnetic force. The magnetic force is generated by a combination. All these things are combinations. Gravity and G1 gravity and G2 gravity are combinations of the gravitic fields and the level 1 object. Magnetic force is generated by the combination of G1 particles controlled by G2 gravity that develops around a special level 1 object. Now, it's not just any level object in this case. A magnet, a planet, coil of wire, a nail, you put DC current through a nail. All of these objects can develop a magnetic force around them, but you need 3 things. You need the the G1, G2, and the object itself. The force behind the magnetic field is G2 gravity. That's why it's so strong. G2 gravity is controlling the flow of G1s flowing around and through the magnet. But the Earth has a magnetic field also. And this is just a typical picture. And one thing I like about this is they actually put the North Pole at the physical South Pole and the South Pole of this magnet to North. Well, this is only conceptually that there's a magnet there, but it helps visualize what's going on. The direction of the flow is based on current flow, not particle flow, and so G1 particles flow the other way, but that's sort of a moot point. As far as the particle model is concerned, we have G1 particles flowing into the South Pole out of the north, going around in all directions, and it's the net G2 force. F2 is my way of saying that there's a net force out here controlling the direction and the speed of the magnetic field. And the Earth has a magnetic field, and lots of other objects do. So now I'm going to get into a little bit of attraction and repulsion. It's a strong force surrounding both magnets that pushes the magnets together, overcoming the weaker force. That's supposed to say force of repulsion. And you got, but in this case, there's a F2 force, a net F2 force, and in particular, it's very strong along this path. And even though there is some repulsion of here in some of the flow, this one comes all the way around and interacts with this one, and the same thing over here. And the same thing, so there's a minimal amount of repulsion, but the primary force is two strong F2 force pushing them together. Remember I said all forces are pushing forces. And this is a attraction showing here, and I'm saying repulsion is happening out here somewhere, minimal, but this is the same flow, even though they look like they're together and are colliding in some sense, but they're just flowing straight through. And these are the two forces, F2 force. There's F2 forces all the way around, but the thing that pushes them together is the very strong force in line here. And then you know, man, they come really, really fast together. In almost all cases, even when I describe gravity, there's a force pushing up and a force pushing down. There's more particles pushing down than pushing up. You end up with a net force. Always opposing forces exist in nature, and this is the case. There's the pushing force pushing together, and there's a pushing force when these streams of particles hit each other. And that's what happens in repulsion. When two magnetic fields interact, the G1 streams collide. They're collide, and they're being controlled by the G2 force. They're being tightly held in that field. And when they hit, they push each other back like two fire hoses pushing each other back. So there is collision. There's repulsion up here because some of these fields, when they get up here, they hit each other and push each other apart. And yet, at the same time, there's a force trying to push them together. The question is, which one wins out? And the repulsive force of these magnets is much stronger. And if there are more repulsive forces, there's all kinds of repulsive force here. As shown. By the way, again, this is current flow, not particle flow. And this is my own drawing of the same thing. You see, you have red is where the repulsion is, and here's the repulsion, and this is south to south, and this is down here is north to north. They both repel. Both forces are there, repulsive and the pushing forces. This is a pushing force when they hit each other, that they're pushing against each other. But the fields are tightly held by the F2 forces around the magnet. The magnetic force is generated by the combination of the G1 particles controlled by G2 gravity. This is just a repeat of my other one. And just to emphasize, to summarize it. Now, here's the summary of the TPM forces. These are the forces you can't see. Not talking about mechanical forces or force caused by wind or water. We're talking about these invisible forces. And TPM has two gravity forces, G1 gravity, G2 gravity, and one magnetic force. Now, you theoretically could have more, as I said earlier, you could have a third gravity. And if there was a magnet at level 2, theoretically you could have a magnetic force at level 2, but there's no evidence that I have that would suggest that that's even possible. Modern science has four forces: nuclear strong force, overcome the repulsive force of the electric force. And they hardly even talk about that. It's not even listed as one of the 4 or 5, but they mention it casually. And now they also, besides the nuclear strong force, they have the electromagnetic force and gravity, as does the particle model. Nuclear weak force is the cause of radiation. Radiating alpha, beta, and gamma rays. And the nuclear weak force is what they say causes this to happen. TPM does not have this force. Radiation in TPM is caused by an imbalance of atomic structure. So if you have a clump of material and some of the atoms in there have an extra electron, then at some point the balance is not right, and that electron will go out, and that's called the beta particle. The nucleuses may have some extra in there, and what happens is when the balance is unbalanced, the forces are just right, it kind of gets pushed out by the G2 force, and that's called the alpha particle. Gamma rays are a little more complex. It's almost as if this object that can radiate gamma rays is collapsing like an earthquake. And so you got multiple atoms, it collapses, and in that mechanical process, it emits peaks of G1s that are the frequency of gamma rays. It's the only way TPM can explain it, but it's not illogical at all. Modern science has 4 forces, should say 5 in my opinion. We only use 3. Could be more, but we only use 3. My name is Bobby Hilster, and I am your particle model guru. If you have a question, Ask Particle. You can send me a question at the email at particleguru@gmail.com, or you can click on the little bell on the website and write a comment or a question. And I appreciate the comments I get, and I try to respond some that I can. Thank you for your attention.